Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, this is a slight change of direction, but again, it's trying to elicit, I guess, how people really play and how can they learn in certain situations. And I guess I'm really interested in if you have sort of a situation of a large number of interacting people, and for example, if you're trying to drive a car or something to get into work, as I am, you've got a lot of choices, and how do you act? What's the best kind of decision to make? In an online market, again, what's the best way? How do people learn in such a situation? And ultimately, I like to know, well, how can you design a system that works really well given the way that people behave? And so this is a talk really with two main elements. First of all, I'm going to give a bit of context, but then talk about some empirical evidence of how people behave in real systems. So if you give them perhaps a slightly artificial game and ask them and look at how they behave, what do they do? And then a slight change of tack, saying a rather prescriptive approach, saying, well, okay, what happens if you look at under what conditions would people come up with a plausible equilibrium? And then just say, give an example of a sponsored search auction. So the previous speakers talked about display ads, and I'm going to talk a little bit about a sponsored search auction. Okay, so some background, just to get everybody on the same page. Not everybody here is a game theorist. So the classical game is something like the prisoner's dilemma. So if Bonnie and Clyde, for example, agree that if they're captured, they'll stay silent, and they are captured and interrogated by the police, then if they both cooperate, in other words, they stay silent, they'll perhaps get off with 1 year in jail because there's not enough to convict them. Whereas if they both if one of them spills the beans against the other, then one will get off free, but the other will get 20 years. And if they both, try to shop each other, they get 10 years in jail. Okay, so this is the classic game. And you can say, and so in terms of Nash, a Nash equilibrium is just a situation where it's in your best interest not to deviate from a particular strategy. So if I've got a set of actions, I take a strategy as a probability distribution over those actions, then my best response in a Nash equilibrium is not to deviate. So for this game here, and the Bayes Nash takes probability distributions. And for this game here, reneging, or if you like, defecting is a dominant strategy, and also is the only Nash equilibrium, renege, when they both be better off, of course, cooperating. So that's a very simple situation of a one-shot game. And the thing to take away, another way to think about that is to say, well, if a player looks at, for example, their best response, and you look at mapping best responses in strategy space, then a Nash equilibrium is just a fixed point in that space. And a Nash equilibrium exists if and only if there is a fixed point. And well, that's a very simple game, a one-shot game. And in practice, you want to look at more complex games. I'm particularly interested in kind of repeated settings. And the most general game you can think of is a stochastic game, where at any point you can move to another game dependent on the actions of somebody. So this just shows it pictorially, where you can see that you're going potentially from this payoff to this payoff depending on the actions of the players. So this is a very general setting which includes, basically it's a game where you're allowed to make transitions that depend on the state. And it includes things like repeated games, where you play the same game a number of times, and also Markov decision processes. And again, I guess the interesting thing to note, so if you imagine playing this situation repeatedly, and you discount utilities, okay, then certainly a Markov strategy is something that only depends on your current state, it has no history over time, then a Nash equilibrium, Markov perfect equilibrium always exists, provided you discount. So that's the kind of result that, again, their existence. The trouble is finding it can be very complicated, and it's not sort of clear if you can really do it in practice. So that's at the end of the theory overview. But just to kind of hold in mind this thing that think about a stochastic game where you can move over it, where you play repeatedly over time, and in some sense a Nash equilibrium exists. But what does it mean? Okay, so now but what happens in large systems? This really isn't practical in a large system. If I'm driving a car, I can't really know what everybody else is doing around me and make predictions about them. I tend to use very limited information about it. And how do people behave in practice? So what would you like an equilibria, what would I like an equilibria to be? Well, I like it to be stable and computable. If you can't compute it in finite time, then what does it mean? And for players who are in some sense boundedly rational, you don't have to be perfectly rational. I need to, in some sense, have some limited rationality. So that's what I'd like to look at. And of course, the question is, well, what kind of equilibria exist that satisfy that? And perhaps one example of something that is sort of semi-plausible is something like fictitious play. So that says, well, I just observe what other people do in terms of their distribution, their distribution of their actions characterize what they do. I'll have some prior beliefs about what they do, and then I'll just play a best response given my beliefs. Then I'll observe what happens, and I update it, and I play it again. Okay, so this is a very relatively simple algorithm, and you can show that in some sense it will converge in some senses, but it converges to outcomes that might not be the same as a Nash equilibrium, or there's certain technical points. But I mean, it's a kind of plausible strategy, and sort of it mimics in some sense what you might be able to do if you kind of localized your knowledge. But what do people really do? Okay, so let's now look at some very stylized games and just see what happens. So the first game is a classical strategy game called Colonel Blotto. So for those of you who know Risk, it's kind of a precursor of Risk, and the basic idea is you're given a set of troops and a set of territories, and so I play against you, for example. I assign my troops to the territory, you do, then we compare them. And whoever has the most troops on that territory wins the territory, and the ones who wins most territories wins. Okay, so this was one instantiation of that is this example here, which was done as a Facebook game. So we launched it as a Facebook game, and in this particular setting there were 100 troops. You had 100 troops, and you could see there's 5 territories, and so. As I said, the person with the most troops on a territory wins. And the Nash equilibrium is sort of relatively complex. What's the ideal thing to do if you're playing Nash? Well, it turns out you'd allocate randomly between 0 and 40 troops. The marginal distribution will be to allocate randomly between 0 and 40 troops per territory. But with this constraint, the complicated thing, you need a constraint that your total should equal 100. Otherwise, you're kind of giving away something. And so then the question is, well, what does this mean? This kind of Nash equilibrium. That's if you're playing against somebody, you have to play against an awful long time to sort of take the expected games to come up with this being a Nash equilibrium. So what do people really do? Okay. Well. So this was now some results of looking at how people actually played this Facebook game. So one interesting thing to note is people are not always very rational. So this is a strategy here. So these are strategies where we're sort of looking at equivalence classes. So this class means any time somebody put 100 on one, for example, on one territory and 0 on the others. So this is a strategy which is bound to lose unless you meet somebody who's equally stupid and also puts 100 territories on the same thing, in which case you might win with probability half. So some people just put 100, all their troops on one territory. It's bound to lose. So, well, it might be they're sub-rational, or it might be that they just haven't understood the game. And these are kind of list of types of strategies with the number of times people played them. So, for example, this one here, if you equally distribute your troops across all 5 territories, then this was played quite a reasonable number of times. And this is a kind of a strategy where people just essentially pick 3 territories and put equal numbers, roughly equal numbers on those. And you can see various other strategies down here. So there's kind of people did tend to concentrate on a certain number of strategies, but on the other hand, if you look at the kind of number of times people played a particular strategy, then they just tended to often play the strategy just once. So they didn't play the same strategy many times. So the question is, okay, what should you play? So this is a graph now that plots what people actually did, and So each point here, for example, this point here is this kind of strategy where you just put 100 on one territory. And the arrows represent, arrows joining different strategies represent the probability that you'd beat that strategy if you were to randomize over all possible instances. So as you can see, this has got no arrow going anywhere because you're bound to lose. This is the most popular strategy, which is to put this, this roughly equal amounts just on 3 territories. So you can see it dominates sort of this strategy, but it's always dominated by another one. So if you look at if you look closely, you can see these arrows these lines have got arrows on them, which says whether that will beat that strategy. And of course, you can always beat any strategy in this game. If you know what somebody's playing, you can always beat it. So how do people actually use these strategies in practice? Well, they seem to do some kind of limited learning. So if they played against somebody and the strategy beat them, they perhaps mirror that strategy. Okay. So people seem to have sort of relatively limited kind of learning. Very limited reasoning in the players we saw. They didn't do deep reasoning. Perhaps it was one-step reasoning. This person did this, therefore I will do this to try and beat them. There are some caveats, and that sort of even within this setting, there are certain features that didn't come out that aren't obvious. For example, there's a left side bias, perhaps because of the way that the game was designed, or you had to allocate troops. People tended to put more troops on the left territories than the right, where you expect it to be random. And people also, the probability of winning against somebody they knew was rather different from playing against a stranger. Whether that was because they knew they could win against somebody or isn't quite clear, or whether they were playing deliberately different strategies. And so there's other games we can look at, online auctions later, but this is an example of another game. The issue of the last game, Colonel Blotter, it's actually quite complex to kind of rationalize about. You've got 5 territories, 100 troops, and you're playing repeatedly. So let's think of a really simple game, an all-pay auction. And this is Yoram's going to talk about this later. You can think of this as a model of crowdsourcing, when you put effort in, or putting in effort into a programming competition where only the best person wins. So the general idea is if there's n players and they bid or compete for some item, and we'll assume it's got a common worth, m. Okay, so there's just one prize, and you both agree. Everybody agrees on the value. And the mechanism of this auction is that everybody bids. The highest bid wins, but everybody pays. So even if you lose, you basically lose your bid, your stake. So what's the simplest example of this? Well, think of 2 players. So in that case, the Nash equilibrium, or the symmetric Nash equilibrium, there are others asymmetric ones, is just to bid uniformly between 0 and however much you value the good for. And if you do that, you can see, well, the expected revenue to the person running the auction is just m, and the expected player's utility is 0. They expect actually not to win, to make any net gain on average. Okay, is that clear? Okay, so again, of course, to get people to play this game, you have to disguise it. So this is an instant, again, another example of a Facebook game dressed up as a pirate game called Doubloon Dash, which again which we tried out on live people. And the basic idea is that you had essentially you could bid between up to 10,000. So M is 10,000, and the idea is you had to say an amount, how much you're going to pay for a ship to reach an island, and the more you paid, the faster was the ship, and the prize was 10,000. And so think of this as simulating an all-pay auction, but disguised, and each player had to submit a bid in the range of 0 to 10,000. Okay, and so then we recruited people on Mechanical Turk to play this game. And of course, the trouble is, Mechanical Turk, you have to pay them a participation fee, but then we also paid them a bonus, and the bonus depended on how well you did in this game. In particular, you were paid a bonus depending on your average utility. So use the average utility if you played at least 30 games. So you had to pay 30 games, because then to kind of ensure that people would go some learning. Which means you could earn a bonus of roughly between 0 if you kind of always lost the maximum amount, or 2 if you did the maximum possible win, if you won the maximum possible amount in every possible game. Okay. And that's just a quick picture of the game, which you can play if you want. You can play both these games if you want to go on Facebook, if you want something a diversionary tactic during the lecture. So what do people do? Okay, so we looked at 500 odd players, and they played about 13,000 games. Well, the first thing people do, of course, is they cheat. So we said specifically you can't bid on a small number of simple bids, and we called people who do that spammers, and roughly 50% of the people ignored that. They did do these relatively simple bids, perhaps just to earn income. The other people did was rather smarter. They basically created Sybils. So the issue was they created multiple identities and played against themselves where they'd be guaranteed to win. And roughly something like 25% of the people who didn't, in a sense, spam, did that kind of behavior. So if you take all those people out, what do the rest do? Well, one thing they did was to have focal points. In other words, they tended to bid on very similar, around certain specific numbers. For example, there was a strong bias to bid in multiples of 1,000, and to sort of bid in multiples of 10. People certainly didn't play Nash. We'll look at that in a minute. And they typically overbid. So this is what other people find. This is what happens in these type of all-pay auctions. People typically overbid. And as a consequence, the average revenue was roughly 13,000. That's 1.37 times this amount M, whereas you'd expect it to be M if people were playing Nash. And people received relatively low returns. So, for example, the expected utility to a player was 0. In fact, the average, they received a negative amount. So this is, again, a consequence of them overbidding. This is a graphical description of what they actually did. So this is on the axis here is the amount that the people bid, and here's the cumulative density. This is like a cumulative distribution function. So if they bid a Nash equilibrium, you just have it would just be linearly increasing. Whereas this is the actual cumulative distribution. And you can see it's got these jumps at 1,000 that reflects the fact that they focus on those values. And you can see here the sort of they slightly overbid at the lower end, and then underbid at the lower end, and then gradually overbid as time goes on. So there's very little weight in the middle. Yeah. So and that translates to the difference in expected return. Well, let's try and look a bit detailed at what people actually did. So this is now players' bid distribution. So this is what people did if you tried to cluster them. So if you look at divide the bids into bins, and then just cluster them on the basis of similarity using a simple k-means clustering algorithm. And this just shows average bids and players' bid for two typical clusters. So this is a cluster where people sort of bid, they bid a low bid with relatively high possibility, not much in the middle, and then they bid at the end. And the red line is the average distribution, and the blue lines represent players' distributions. And this is a slightly different distribution here. So you can do this and think about separating people into classes, and they do behave in sort of relatively different ways if you just ignore the time dimension. But what we really like to do is do people learn. So if you see what happens now if people look over time. So you look at people's bids over 4 consecutive games, and you see what happens here. This is the time period here, and this is their average bid. So it rapidly increases, then it sort of wanders around a bit and decreases later on towards the end. I mean, there's a lot of variation, but you can see there's certainly a noticeable increase at the beginning, and then it stays constant and then fluctuates. Yep.
Is it because not many people played 40 games, or is it because it bifurcates?
I don't think it particularly bifurcates. Yeah, that's a good question. I'm not sure. I mean, I guess we're going to look at a minute, trying to disambiguate. The trouble is these don't tell you how people behave. They just tell you, it's just kind of an indicator. What we really want to do is say, what do people really do sequentially? And this is just purely sort of looking at it, over time. Yeah, I don't think it bifurcates. I mean, you've got a mix of behaviors, but that's a good question. So what do people really do? Well, people seem to be definitely affected by winning or losing. So perhaps people are less bothered, less concerned about getting their net income. They're more affected by whether they win or lose. because people behave differently according to whether they win or lose. So, for example, unless their bid is small, then it was statistically significant as their behavior following a win or a loss. So what people did was after if they lost against an opponent, they typically increased their bid. And what that means is that, so roughly, almost everybody, 2/3 of the time, increased their bid after winning, if you conditional on them actually changing their bid. And the reverse effects apply as well. So if they win, then they would decrease their bid. And so that's kind of plausible. You could say, well, if a player wins again, then perhaps she try and increase her utility by lowering her bid while still trying to win. So it's a kind of a plausible, simple behavior. The consequence is, if you kind of look beyond that and try to say, well, did people do something rather more sophisticated? For example, did they have a limited recall? So perhaps they would just look over the past 4 games or 3 games and try and sort of maximize, try and use that information to develop a better bid. Did they do that? Well, it seems as though they didn't particularly. I mean, you could fit some players who did that, but you didn't get, but not very many. I mean, there's some people you could plausibly say did that, but typically not many. So in fact, the only thing, if you were trying to mimic the behavior of an average player, the only thing that fitted it well was a kind of really dumb kind of heuristic, which is the following. So in each game, you say, well, if I won the previous game, then I'll just decrease my bid. And if I lost the previous game, I'll just increase my bid. And we tried various amounts. And if you just pick a number like 1,000, 10,000, 1,000 it should be rather than 10,000, then you get very close you mimic effectively the average pair of what people did. Okay, because this isn't a great strategy. So then what we did, we played this against the empirical distribution. So if you look what people actually did, play this strategy against them, see what it comes out with, you get a return of about minus 2,000, which was the average playoff to people. Remember, this isn't a good strategy. You should be able to get, you should be aiming to get at least 0. So this is really dumb strategy, seems to do well, seems to impossibly mimic what people do. So this is a limited recall best dynamic, which is say, okay, I'll look over a window of history of length d, perhaps d is 1, 2, or 4, and then we looked at infinity for the whole thing. And then we'll choose the bid that maximizes my average return if I were to have used it against all those bids. Okay, so it would be a relatively simple recall dynamics where you're kind of using a limited history and trying to do the best conditional on the past. So that was one thing we tried, which fitted a few people. But and a better thing you could do is say, well, actually, a standard learning approach is to do something like a multiplicative weights update. So what that does, it says, well, I start from some bid distribution, a discrete set. I'll assign uniform weights to them, and then if I win, I'll increase the weight I decrease the weight by some amount, 1 minus lambda, where lambda is some learning rate, and if I lose, I'll increase it. Okay, so this is kind of you're trying to you're decrease it rather. So essentially, you're trying to adjust the weights according to whether you win or lose. Okay, so this is it's the simplest kind of learning thing you can do. Just increase or decrease your weights multiplicatively. And what happens if you do that? Well, if you play that in practice, that does really well against the empirical distribution. You dominate. You get a positive return and do much better than anybody did in practice. Moreover, the previous one, this limited recall dynamics, also did very well. We did better than people did on average. You come up with a positive return. So that sort of says, well, to summarize, people appear not to use anything very clever. They don't seem to use standard learning techniques. They don't seem to use limited recall. Perhaps they do some limited best response, but really dumb. But if you did something more clever, if you gave them some hints, said, well, try looking at the past, or try using this learning algorithm, you do a lot better. Which suggests, well, okay, so first of all, it says people aren't very clever in this setting, and also says you could do a lot better if you kind of gave them an agent to help them. Okay, so now just a flip to say, well, this is a setting and a very specialized. What happens if you try to say how people should behave? Okay, and if people did react to this empirical distribution, what would happen? Well, I'm going to think about a mean field approach, which just says, suppose now I'm in a stochastic game and I just want to maximize my expected return. Then a cognitive strategy would mean I'd have to know everything that was going on, which is kind of implausible. But a mean field approach just says, well, I'd assume there's a large number of agents, and I'll just only react to the average of the average state space and the average strategy. Okay, so then you can come up with a strategy in a sense that only depends on the average behavior of others. So why is that a mean field approach? Well, it's a mean field essentially because you need the number of states to be large. And if you do that, then it says if you've got some distribution of states, such as of f, if I think of the distribution of states as f, then given that distribution, I can define a strategy. And then if that strategy that I so define is a steady state distribution, then I'll have got a mean field equilibrium. So, I mean, in pictures, it's saying if you start from some distribution across states, I'll then find an optimal strategy given that distribution to produce a new distribution. Okay, if everybody plays it, I'll produce a new distribution. And if that's a fixed point, then I'll call it a mean field equilibrium. Okay, so that's, remember we talked about equilibrium as fixed points. This is another way of getting a fixed point equilibrium. So let's apply this again to an auction setting, but rather slightly more complex than the all-pay auction and motivated by a sponsored search auction. So in particular, I'm now thinking about sponsored ad auctions, which is where, not display ads. So for example, if you type something like organic food into Bing, you get these examples of ads which people are bidding to have shown to you. So you've got some on the main line and some on the sidebar. Now the issue is when people bid on these, the advertisers have budgets. The question is, well, if they knew their budgets or if you knew them for them, how should they bid optimally, and what should you do? And this is just to say people behave very differently. So these are real keywords such as coupons, BlackBerry, and this just shows the probability of bidding an amount if you take the bid divided by the budgets of various advertisers. I mean, the thing to notice is that they're very different. You know, they don't have a common shape. People behave differently. The markets behave very differently. So the traditional game theory approach would be to assume that your number of bidders is known, you know everything, and so then you could work out this big Nash equilibrium, work out what to do in all these situations. But that's clearly just unrealistic. I mean, for a start, the system's very noisy, and also you just cannot possibly know. There's too much information to parse. So let's try and look at this kind of stylized model now. Suppose we look at budgets, bidders who are constrained by budgets, and they want to maximize their return in a repeated auction. Okay, so that's equivalent to an online stochastic knapsack problem. And I'm going to assume there's just a single good, and the user has some budget B, some value V, and can bid some amount A. So think of A as your action. Okay? And I'm going to assume that the winner pays the second highest price. It doesn't matter too much. But they pay some amount P. So that means my private valuation, which I know but other people don't, is V. And I'm assuming there's some competing bid that's not observed, okay, P in this case. So then my decision variable is what to bid, which will depend on both my value and my budget. And how much do I gain? Well, if I win the good, then my net return is just the value minus what I paid. In other words, V minus P. And remember, I pay the second highest price. In other words, the highest bid, a competing bid, okay? And so if I want to express this as a problem, I can say, well, I want to just maximize my expected discounted return. And now I'm going to make a big assumption. I'm just going to assume for the minute that bids are actually identically distributed with a common distribution. Okay, that's a big assumption, but I can perhaps appeal to mean field limits to justify that. So then the trick is to actually do a kind of joint space and time scaling. So if I scale both time and space, in other words, I scale the discount factor by letting the beta go to 0, and at the same time divide the budget. So essentially, I let beta go to 0 and divide the budget by beta. So this is this joint scaling. If I do that, it turns out I can produce a really nice result that says as the system gets large, then the best thing for me to do is just to bid is to shade my bid according to this factor 1 plus v prime b, where v is actually the a value function. And that holds true regardless of what kind of auction I'm dealing with. So if I'm dealing with a second price, generalized second price, or first price, I should always shade my bid by this amount, and I should bid what I would have done with that value dependent on the auction. So, for example, if I knew how to bid in a generalized second price auction with value v, I would just shade my bid by v by that amount. Okay, so there's a nice characterization. And you can show actually that to show that you get a mean field equilibrium out this, you have to do a kind of lot of dancing, if you like. You have to dance around a bit and create something slightly strange. You have to divide the budgets, the bidders, into groups of budgets, into classes of budgets, and essentially allow a resetting of budgets to get the machinery to go through, which is kind of a bit of there's a bit of kind of murkiness there. So I'll skip over that. But essentially, if you imagine that you restrict yourself to policies that are the same modulo restarts. In other words, if I can randomly reset my budget, then you can show a renewal equilibrium is something that does that, and you can show that one exists in this setting as you let the number of players go large. So this is a mean field equilibrium. So in other words, what's that saying? If I look at the distribution of my highest opponent's bids, then a mean field bid such that I can bid according to that. Okay? And so this works if there's a lot of auctions per period. Okay? So my optimal strategy, in other words, is such that I bid against this maximal bid of my opponents, and that turns out if everybody does that, that will create the same distribution. So then the question is, well, okay, that's very nice in theory. Suppose I'm an advertiser. Could I ever possibly implement this? Suppose now I'm an advertiser rather than the platform. So the problem is that I don't know my opponent's distribution. So what could I do? And they face an interesting dilemma, because if I bid in an auction, I get a censored observation. So if I win with bid B, okay, then I know that the price I've paid, I know exactly assuming in this case I know what the price is paid. Okay. If I lose, then I don't know. All I know is the price was above what I bid, so I would have to increase my bid by some amount to win. Okay. And of course, in practice, you're only charged if an ad is actually clicked. So how can you deal with this? Well, one way around this is to use essentially the Kaplan-Meier estimator, which deals with these censored observation. So this is a censored observation because you've only essentially got information on one side. And if you do the Kaplan-Meier estimator, you can think of that as something like a product limit algorithm. So what I could do is imagine you plug that into an algorithm to estimate my distribution function f, and then use this thing that I know, my characterization of the true control given f, to calculate what I should do. And then you can do some work with long tan shown. If you do that, you can show as a regret algorithm that will achieve something like that. Will achieve root t regret if you assume that the KM Kaplan-Meier estimator converges suitably. So this greedy product limit algorithm is to say, well, I'll maintain an estimate of f, and then I'll bid according to maximizing my, essentially choose the bid that will be the optimal bid for the setting for the value function if I knew that distribution with remaining time t left and budget b. I then receive a censored observation of this kind of distribution f, and I update that and I go round. Okay, so that's a relatively simple algorithm. The trouble is it can be quite expensive. So a simple thing to do is say, well, I could separate my exploitation and exploration phase. So suppose instead I'll just use a bid randomly for a period of time to see what happens, and then I'll just use that. I'll use that then to estimate the distribution, and from then on I'll just fix my knowledge at that time and just use the bids from then on. Okay. So for the first period of time, I just randomly bid. And then ever after this period of time, epsilon t, I estimate the distribution and then just calculate the optimal bid using that estimate and not updating it. Okay. So for the remainder of the time, I just use this to bid so I don't update the distribution. So that actually achieves slightly worse regret, something like order t to the 2/3. but you win in terms of complexity. So that's the kind of trade-off you might be able to make in practice. We tried various experiments looking at, first of all, where we constructed a distribution from AdCenter data, being ads, and simulating the model. And the second one was just violating all the model assumptions, just replaying historical data to see how this performs sequentially. And it does pretty well. I mean, it's surprisingly well. So this is just this is the theoretical ones I'm going to show you now. If you compare it to an offline optimal algorithm, which is more than you could possibly ever do. I mean, an offline algorithm has to know what you would bid. You'd have to know how to bid given essentially history of the future that you can't see. But you can see the competitive ratio of something like this greedy product limit is pretty high. It's about 90%. So you do pretty well compared to just doing something like Q-learning, which actually does worse. Even so, the standard machine learning technique does less well in this case because you're not making use of the characterization, this simple characterization of the optimal control. And simple budget smoothing, which would be to smooth your budget out at a constant rate, does pretty poorly. And lastly, just to talk about sort of, again, this performance complexity trade-off, which might relate to how can people, if you think about how people learn in situations, you need to solve your compute time problems. So this generalized product limit performs reasonably well. It has a kind of good competitive ratio. And this epsilon first thing, where essentially you kind of only learn for a period of time. So it's got larger regret, but it runs a lot faster. So that's the trade-off. Essentially, it can run 5 times faster, but you're losing 10% of the accuracy. So that's the trade-off. So this is just an example here. This is an example of a distribution of market price as a percentage of the maximal budget. And these are just various algorithms playing out over time, where this is the competitive ratio, so 1 would be ideal. And this greedy product limit, you can see, is achieving about 90% of the optimal, whereas something like this epsilon first is losing another, is 10% down on that. But if you look at the time it takes, the CPU running time in seconds, then the problem is this greedy product limit, as your percentage of budget remains, just really shoots up, whereas the epsilon first is kind of constant cost, so it's way down there. So you've got this trade-off. So the issue there, I think, is what happens in practice. And if you're trying to think about how people do, what do they do? Did they do this trade-off, or are they doing something different? So this is a kind of, I guess I've tried to sort of address this problem of how do people learn in practice and how do they learn in automated systems. And there's basically, at the minute, there's a rationality gap, or there's a big gap. These are just kind of steps along the road. In one sense, we know how people learn in simple systems, and they clearly don't behave according to well-known Nash equilibrium in complex situations. They seem to do some limited learning, but very often very naive. So in these large systems, you've got the question then, well, should you actually help people? Can you give them a kind of hint as to push them more in the direction of doing something like best response? And if you do that, you can certainly show that if people did that an equilibrium would exist. But I guess the challenge is to come up with computable and credible strategies. And really what I'd like to do is to complete the loop, to link these models to strategies that people actually do. Because at the minute there's a gap. There's a gap between the models of what people do and what they really do. So this is just steps on the road. And I think I'll stop there.